On April 20, 2010, Deepwater Horizon did not fail because one giant machine suddenly broke. It failed because several smaller defenses weakened or disappeared in sequence. Cement beneath the seafloor did not hold. A pressure test produced warning signs that were accepted as normal, and heavy drilling mud was then replaced with lighter seawater, reducing a major pressure barrier. When hydrocarbons began rising, the influx was not recognized soon enough, and when the final emergency device was needed, it could not seal the well. 11 workers died, the rig sank, and oil flowed from the Macondo well for 87 days. The disturbing part is that there was no single instant when disaster became inevitable. There were several moments when a different interpretation, a pause, or a working barrier might still have changed the outcome. So how did a routine operation near the end of a drilling job become the largest marine oil spill in United States history? Deepwater Horizon was a mobile offshore drilling rig working on the Macondo well, roughly 50 miles off Louisiana, in about 5,000 feet of water. BP operated the well. Transocean owned and operated the rig. Halliburton performed the cementing work. That division matters because deepwater drilling depends on specialists, contractors, procedures, and handoffs. If one group sees a risk differently from another, a small misunderstanding can travel far. By April 20, the exploratory well had reached its target. The next task was temporary abandonment. Secure the well, remove the rig, and leave the site for later production work. Deep below sat a reservoir under enormous pressure. Heavy drilling mud inside the well helped push back against it. Think of the mud as a tall column of liquid weight. Reduce that weight too early, and the reservoir gets a vote. Before the mud could be displaced, another barrier had to be trusted. Cement had been pumped around the production casing near the bottom of the well. Its job was to isolate oil and gas from the wellbore. Investigations later agreed on the central point. That cement barrier did not prevent hydrocarbons from entering the well. The exact physical mechanism was debated, but the practical result was clear. The barrier was not holding. Even then, disaster was not inevitable. A failed cement barrier should be detected before another barrier is weakened. That is why the crew performed a negative pressure test. The idea sounds simple. Lower pressure inside the well and watch what happens. If the barriers are sound, the well should remain stable. If reservoir pressure pushes fluid into the well, something is wrong. In effect, the test asks, are we truly sealed? That evening, the answer was not clean. During testing, pressure on the drill pipe rose to roughly 1,400 pounds per square inch, while another line showed no flow. Those readings did not fit together neatly. The mismatch demanded a convincing explanation before work continued. Instead, the pressure was attributed to what some on the rig called a bladder effect, an explanation investigators later rejected. The test was eventually treated as successful. That became one of the most important decisions of the disaster. The well had produced evidence that its barriers might not be secure, but the evidence was interpreted as a testing oddity rather than a warning from the well. This is one reason complex accidents are difficult to recognize from inside. Nobody receives a flashing message saying, "Catastrophe begins now." They see a strange gauge, a result that almost fits, or an explanation that sounds plausible enough to keep moving. With the test accepted, the crew continued temporary abandonment. Heavy drilling mud in the riser began to be displaced with seawater. Seawater is much lighter, so as the fluid column became lighter, hydrostatic pressure on the well fell. That step was planned. The danger was the assumption beneath it. Displacing the mud made sense only if the cement barrier had truly passed the test. Imagine a door with a weak lock. The heavy mud is someone leaning against it. Replacing mud with seawater is like stepping away because you believe the lock has been checked. If the lock is broken, the door does not care what the checklist says. Oil and gas began entering the well. Drillers call that a kick. A kick is serious, but not automatically a blowout. Detected early, it can often be controlled. For a time, however, the influx was not recognized. There were clues in pressure, flow, and fluid volumes. But the rig was also handling changing operations and multiple streams of information. The crew did not identify the well as flowing until the situation had advanced dramatically. Then physics started working against them faster. Hydrocarbons rising from deep underground encounter lower pressure. Gas expands. A relatively small gas volume far below can become much larger near the surface. The well was no longer quietly taking in formation fluids. It was unloading upward. Drilling fluids surged onto the rig. The crew tried to divert the flow, but part of it was routed toward the mud gas separator. That system was not designed to handle a blowout of this magnitude. Gas reached areas of the rig where ignition sources were present. At about 9:49 that night, explosions tore through Deepwater Horizon. The rig became an inferno. 11 workers never returned home. 17 others were injured. Nearly 100 people escaped from a burning structure above a pressurized well in open water. Deepwater Horizon burned for roughly 2 days before sinking on April 22nd. But the sinking did not end the emergency. The drilling riser collapsed to the seafloor, and oil continued escaping from Macondo. Now the final mechanical barrier mattered most: the blowout preventer. The blowout preventer, or BOP, was a massive stack of valves and hydraulic rams on the wellhead. Its last resort blind shear ram was designed to cut drill pipe and seal the well. It sounds like the ultimate emergency brake. But an emergency brake only works if the system reaches conditions it was designed and maintained to handle. Early explanations made the BOP failure sound simple. It should have closed, but it did not. Later engineering investigations showed a more complicated failure. The drill pipe inside the BOP had likely buckled and moved off-center during the emergency. When the blind shear ram activated, the pipe was no longer positioned where the blades could cleanly cut and seal it. The ram damaged the pipe, but the well remained open. Investigators also found problems involving parts of the BOP's control systems: testing, batteries, wiring, and maintenance. Not every defect directly caused the final failure, but they revealed something larger. The supposed last line of defense contained weaknesses before anyone desperately needed it. That is why Deepwater Horizon cannot be explained by saying, the BOP broke. By then, the safety chain was already collapsing. The cement barrier had failed. The negative pressure test failed as a decision point. Mud displacement reduced pressure. The kick was recognized too late. Emergency handling did not contain the flow. Then the final mechanical barrier could not seal the well. The technical chain matters. The organizational chain matters just as much. BP, Transocean, Halliburton, and other contractors worked within overlapping responsibilities. Investigations found weaknesses in risk management, communication, recognition of critical indicators, and the handling of operational changes. The temporary abandonment plan had changed several times before April 20, without a sufficiently robust process for evaluating all the changing risks together. That does not mean every individual choice looked reckless. Many looked manageable. Some saved time. Some simplified the job. Some resembled practices that had worked before. The danger came from how those choices interacted. One decision trims a safety margin. Another accepts an ambiguous test. A third removes a barrier because the previous barrier is assumed reliable. No single step feels like the whole disaster. Together, they create a system with less protection than people realize. That is the deeper lesson of Macondo. Complex disasters can grow from decisions that look locally reasonable. After the rig sank, remotely operated vehicles worked nearly a mile below the surface. Engineers tried one method after another. A containment dome failed when methane hydrates clogged it. A tube inserted into the damaged riser captured some oil. A top kill attempt pumped heavy fluids downward, but could not overcome the flow. Eventually, a capping stack stopped the visible leak in July. Relief wells later allowed crews to permanently seal the Macondo well. By then, oil had flowed for 87 days. Millions of barrels had escaped from the reservoir. Federal estimates placed the total discharge from the well at roughly 4.9 million barrels, although some oil was captured before reaching the Gulf. Oil spread across open water, reached shorelines, entered marshes, and affected habitats used by fish, birds, sea turtles, marine mammals, and countless smaller organisms. The damage appeared at different scales. Oil coated wildlife and shorelines. Subsurface plumes exposed deep water ecosystems. Fisheries closed across large areas, hurting communities tied to seafood and tourism. Then came a harder question. What does recovery mean across an ecosystem this large? Some effects were visible immediately. Others required years of monitoring. Restoration became a long-term effort involving wetlands, wildlife, water quality, habitats, and lost public use. In 2015, governments announced a civil settlement with BP worth more than $20 billion, including major restoration funding. But money could not rewrite April 20th. The more useful question was whether the system itself would change. It did, although no regulation can remove risk entirely. Before the disaster, the Minerals Management Service combined missions, including offshore development, safety oversight, and revenue responsibilities. Afterward, those functions were separated. New organizations included the Bureau of Ocean Energy Management, the Bureau of Safety and Environmental Enforcement, and the Office of Natural Resources Revenue. New drilling rules strengthened requirements involving well design, cementing, pressure testing, and blowout preventers. Safety and environmental management systems became mandatory for offshore operators. The goal was broader than tougher hardware. Regulators also wanted better management of operational and organizational risk before unusual signals became emergencies. That distinction matters because safety cannot be engineered by buying one heroic machine. It requires barriers that are independent, tested, understood, and respected. It requires crews who can stop when data does not make sense. It requires contractors to share the same picture of risk. And it requires procedures that treat unexplained pressure as information, not inconvenience. Deepwater Horizon also changed expectations around blowout preparedness. Operators faced stronger requirements for containment, emergency planning, BOP reliability, and proof that critical equipment could perform when needed. None of that makes deepwater drilling simple. Equipment can fail. Humans can misread signals. Organizations can become comfortable with deviations, because yesterday's deviation did not cause a disaster. That last point is especially dangerous. If an abnormal reading appears once and nothing happens, people may call it harmless. If it appears again, it becomes familiar. Familiarity starts to feel like evidence, even when it is only repetition. Eventually, the abnormal becomes normal, right up to the moment physics refuses to cooperate. Deepwater Horizon was not created by one spectacular mistake. It emerged when multiple protective layers lost strength at the same time. A cement barrier failed. A warning test was rationalized. Heavy mud was removed. A kick grew without being recognized soon enough. Emergency systems then faced conditions they could not successfully control. Each step narrowed the path back to safety. That is why the most useful lesson is not never make mistakes. Complex systems will always contain imperfect equipment, information, and people. The real goal is to keep one mistake from requiring the next mistake to remain harmless. Good systems assume that something will fail. Then they make sure the next barrier is strong, independent, and difficult to explain away. On April 20th, 2010, Macondo had many barriers on paper. At the critical moment, it did not have enough barriers still working in reality. And that is what makes Deepwater Horizon worth studying today. Catastrophe rarely arrives carrying a sign that says, catastrophe. More often, it arrives disguised as a strange pressure reading, a shortcut that worked before, a plan change that seems manageable, or a safety device everyone assumes will save the day. The explosion was the moment the world saw the disaster. The disaster had begun much earlier, when small warnings stopped feeling important.